In this video, we'll prove the fundamental theorem of calculus, part 1. Here's the statement of FTOC part 1. We need f to be a continuous function on an interval AB. Notice the interval AB is closed. Then for any input x in this interval, we're going to define a function capital F to be the integral of continuous little f from a up to x. The conclusion is that this capital F is an antiderivative for the integrand little f. In other words, taking a derivative of capital F will result in little f of x. To prove the theorem, we'll need a few different things. Here are some that we'll go over in this video. Let's go through the list. First, the extreme value theorem. Let's read through this statement. Notice that the condition for EVT is that f be continuous on a closed bounded interval. Here is an interval. We use square brackets to indicate that we want to include the endpoints a and b. All values between a and b are part of the interval, including the endpoints a and b, means that the interval is closed. The notion of bounded, in other texts you might see it stated as finite. This can be verified by looking at the value b, subtracting the value a, and getting a number. In other words, not infinity. If we have f satisfying those conditions, then we can find a point, c sub m. We can also find a point, c sub capital M. The lowercase m corresponds with the output being an absolute minimum on that interval, and the capital M corresponds with the output at that c sub m being an absolute max. This is EVT. We also need the intermediate value theorem. Here's the statement. Notice that the assumption on f is exactly the same as it was in EVT. In other words, f is continuous where on a closed finite interval. What is the conclusion of IVT? It says that if we have any value between f of a and f of b, then we can find an input on this interval such that the output of the nice f is exactly that value k. Note that f of a and f of b may be the same value, by which we can only make a conclusion that f produces the output f of a, f of b. It may be that f of a is larger than f of b, for which we are guaranteed for any value smaller than f of a but yet bigger than f of b, there's an input which produces that output. The third case might be that f of a is smaller than f of b, for which all k values bigger or equal to f of a and less than or equal to f of b, there's an input producing that output. So that's IVT. We'll also need a comparison theorem. Note once again that our f has a similar condition. It's required to have a condition on the closed bounded interval a to b. The condition here, however, is not continuity but integrability. In other words, the area under the graph of f on this interval is defined. It's integrable. Next, let's look at what the comparison is. We want to find a small value little m and a big value capital M, those are constants, such that the output of our function is bounded between those two values. If that is the case, and we throw an integral over here, throw an integral over here, well, that's finding the area of a rectangle of height m on this interval. So that's capital M times the base b minus a. Throw an integral over here, that's the height of the rectangle little m times the base b minus a. And then throwing an integral over here is exactly that expression. Here's a visual of that idea. Two rectangles, one of height capital M, one of height lowercase m, and some interval a up to b. Clearly, the area under the blue line is larger than the area under the orange line. Throw in a graph where the graph always sits above the orange line and sits below the blue line, and then the area under that graph over the interval a to b will be smaller than the area of the rectangle in blue, but larger than the area of rectangle in orange. So that's a comparison theorem. Last thing that we're going to need is a couple of properties of integrals. Let's suppose that we have a nice function f that we can integrate it. Then if we set up the integral of f where the bounds of integration are set up in one way and we swap the bounds of integration, then that's going to come at the cost of a minus sign. A second property of integrals is that if we set up the integral, we can break up the integral in any way that we like, provided that these two expressions make sense. Oh, one more thing. We're going to prove our fundamental theorem of calculus part 1 using this theorem here. The MVT is a theorem covered in first semester calculus, and this idea of the mean value is also known as the average value. And if you look at this right-hand side here, this is finding the average value of this function over the interval from a to b. All right, let's look at the statement. Hey, once again, we have the requirement that f be a continuous function on a closed bounded interval. Very nice. What's the conclusion of MVT for integrals? It tells us that there is an input on that interval such that the output at that particular input is exactly the average value of the function over that interval. So we're getting an average value in the form of an integral. Okay, let's prove this MVT for integrals. Here's the statement that we just read, and here's the proof. We're going to see that there are three pieces that we can look at. Let's first start off by using that assumption that the function is the function is continuous on a closed bounded domain. That is exactly the requirement of the extreme value theorem. Hence, the function will have extrema at little m, an extrema of little m and capital M. Here's that statement. Then we can exactly use that statement to set up the comparison theorem. We can restate that at every point the outputs are bounded between these values to say that if we add up all of those outputs, that it will be bigger than adding up all of these outputs and smaller than adding up all those outputs. Manipulate this in a simple way by dividing through by b minus a. We come up with this expression. And then this expression here, we can let k equal this value that sits between little m and capital M. And then, since f is a nice function that we can apply IVT to, we can conclude that there will be an input which provides output exactly equaling k, and that is exactly the statement of MVT for integrals. Very good. We're now ready to prove the fundamental theorem of calculus. Here's the statement. We have a good function, and we want to show that that good function has an antiderivative. Recall that the idea of an antiderivative is when you differentiate the antiderivative, you get the original function, little f. That means that we're interested in finding what the derivative of capital F is. We want to show that we get it equal to little f. So let's start by writing down capital F prime. That means the derivative of capital F. So we don't have to know anything except how to define a derivative, and here's the definition of a derivative. It's the limit of a difference quotient. So we're going to take a small little change of our input x and see what the function does a little bit away from our x and at x. This is two quantities being divided by h. That's the same thing as two quantities being multiplied by 1 over h. The two quantities, let's go ahead and look at how our capital F is defined. Let's do the easy one. Capital F of x is exactly this integral here. But if that's capital F of x, then capital F of some different input, all we have to do is change the upper limit to that new input. Next, what we'll do is we'll use a property of integrals, and if we change this lower bound a to that upper bound x, that's going to come at a cost of changing the minus into a plus. So that gives us this expression. If we combine the two integrals, since the lower bound on the first integral matches with the upper bound on the second integral, then we'll get a single integral with lower bound x and upper bound x plus h. So that's produced here. Now, if we concentrate on this quantity we're taking a limit of, we see that 1 over h is the same thing as the upper bound minus the lower bound. And thus, this quantity we're taking a limit of is an expression for which we can apply MVT for integrals. And MVT for integrals, that theorem tells us that there is an input which gives us exactly the average value, which is this expression here. So that's stated here. I have this funny notation, c sub h, to tell us that this input will depend on the h that we pick. And you can clearly see that as h goes to 0, at some point x plus h is going to be a smaller quantity than c if we just fix our c. Hence, c sub h must depend on h. And then if c sub h depends on h and you let h go to 0, then the only choice for c sub h is to become x. So let's take a look. MVT for integrals. Swap this out for f of c sub h, that's produced here, and then make the argument that c sub h, as h goes to 0, has no choice but to become x, and then that established this equality, which is going to finish the proof because we now have that the derivative of capital F is little f. In other words, capital F is an antiderivative for little f. Beautiful.